Okay, Michael, so enough of all this hand waving you like to do. Let's actually write out some equations.
Okay.
Yeah, there's no need to fear the equations, Michael. So I'm going to leave our little picture up so you can remember what it is we're talking about. And I'm going to leave up the definition or the tuple part of what an option is so that you'll remember that. And then I'm just going to write an equation up here. And here it is. So v sub t plus 1 of s equals max over O of the quantity r of s comma O plus sum over s prime of s of O, s prime times v sub t of s prime. What does that equation look like to you?
Well, it has a lot in common with the Bellman equation.
Right. And in fact, that's exactly what it is. It is a rewriting of the Bellman operator. So what do you think the various constituent parts are?
Well, I don't. Maybe an easier thing to do would be to explain what looks like it might be different.
Okay.
So, for one thing, A has become O
hmm
because I guess actions have become possibly temporally extended actions
Or options.
or options. Good. Do we need to include A in there as well? Like, why how can we ignore all the A's?
Well, because the A's are inside the O's.
The A's are inside the O's.
Yes.
There's actually an O inside an A.
Well, I think that depends upon whether it's a lowercase or capital A.
That's fair.
Thank you.
But I still don't quite understand. Like, so you're saying options are made out of actions,
Yes, because they have little policies.
but can you have an option that is just an action?
Of course, right? So options are a generalization of actions. If I wanted to take an action and I wanted to turn it into an option, then the initiation set would just be everywhere where that action is valid. The policy inside that option would just say for whatever state I'm in, take that action with probability 1 and all other actions with probability 0.
Mm-hmm.
And then the termination probability would be 1 for all of the states that I can reach from that particular state to a particular action. Actually, it would just be 1 everywhere.
One everywhere. I see. I see. Oh, that's okay. That's actually really cute. That kind of helps me understand why these three quantities are the way that they are. So it allows us to specifically say, oh yeah, well we can always include an action which is a primitive action that just you can use it wherever you can use the action. It just does the action and then it stops right away.
Right, exactly.
Okay. All right. Good. So then the O. Okay, I get the O's generalizing the A. Then another difference is there's no discount factor that I can see. And then the last difference is that you seem to have spelled T as an F.
Right. Well, F and T are the same for an appropriate kind of thinking about
Only in
the
logic.
Only in logic?
Yeah, T and F are the same.
Actually, they're the opposite in logic.
Oh, whoops.
Yeah. T is true and F is false. I hadn't thought about that. That's kind of a interesting thing that we could talk about for an hour and a half. Or I could just explain to you what F is. So you did the right thing. You noticed that we still have a reward function as we did before in the Bellman operator. We still have value functions. That's what we're trying to do. We're trying to update value over states. We have the little S's and the S primes. The O's are basically A's, so that doesn't seem different. But the two big differences are a lack of a discount factor, which isn't quite true. We actually have a discount factor, but it's hidden. And instead of a transition model, we have F. So F is, if this really is a Bellman operator, F is sort of, I think, clearly playing the role of a transition function. It's somehow telling you something about states, options, and next states. And what I really need to do to make this clear, I think, is to just really write out what F is.
Oh, that would be super helpful.
That would be really nice. But it turns out that I have to write out something else as well, and that is R. So R looks sort of superficially like the reward function that we've had before, although in this case the reward is from, taking a particular option in a particular state. But actually, this reward function is hiding a lot of complexity as well. And to see what that complexity is, I think it helps to draw a picture.